In this video, we're going to look at what effect does the second derivative have, or what can we say about a function by looking at the second derivative of a function. Let's take a look at some graphs. Here we have a graph from A to B, and look at the tangent lines. If we draw in the tangent lines from A to B, the tangent lines are beneath the curve, but they are increasing. So we can see the curve is an increasing function because the first derivative, the slope of the tangent lines, are positive. But what do you notice about the rate of change of the slope of the tangent lines, which would indicate we are talking about if we're looking at the rate of change of the function, we're looking at f prime of x. But what if I want to look at the rate of change of the derivative? Which means, looking at these tangent lines, what's happening to the slopes? We can see that they're increasing. So if we're looking at the rate of change of the derivative, we're looking at the second derivative. And here, for this graph, we can see that, for instance, if I said the slope of this line was 1/2, the slope of this line was 1, the slope of this line maybe 2. You can see that the slope of the tangent lines from left to right are increasing. These values are getting larger. They're increasing. Let's take a look at another graph. Again, if we looked at the slope of the tangent lines, we know this function is increasing, so the slope of the tangent lines are going to be positive. But let's again look at the slope of the tangent lines and how they are changing. The rate of change of the tangent lines would be our second derivative. And again, if I just estimated the slope of these tangent lines, let's say the slope of this tangent line is 2, maybe the slope of this tangent line is 1.5, the slope of this tangent line is, let's say, 1/2. We see that the rate of change of the tangent lines is getting less. They're decreasing. So the second derivative is going to tell us something about the shape of the graph, whether it be concave up or concave down. If the rate of change of the tangent lines, as over here, are increasing, it's concave up. And notice the tangent lines are beneath the curve. But in the second graph, the graph we can see is concave down, and the slope of the tangent lines are decreasing. And we notice that the tangent lines are above the curve. So this should indicate that we are going to be using the second derivative to determine the concavity of a function on an interval. If we can determine the slope of the tangent lines, the rate of change of the slope of the tangent lines is increasing, it's concave up. If the rate of change of the tangent lines are decreasing, it's going to be concave down. If the graph of f lies above all of its tangent lines on an interval I, then it is called concave upward. If the graph of f lies below all of its tangent lines, it is called concave downward. And you can verify that if you went back to the previous slide. Now this is saying if the graph lies above the curve, it's concave upward. And we saw that in the last graph. That was our first graph. The second graph, the graph was below our curves, our tangent lines, so the graph was concave downward. Now, just looking at this graph, can you identify the intervals where this is concave upward and where it is concave downward? Now, with this graph, I tried to make this come to a point, not rounded like it shows there. Imagine this coming to a point. So let's look at just being able to identify where this graph is concave upward and where it's concave downward. So let's look at those intervals. Now CD I have as concave down. Here we would be concave upward. Concave down. Concave up, because this comes to a point where I drew that point in. I didn't want it to round off like it shows in the graph. I wanted it to come to a point so the concavity doesn't actually change. And then we have concave downward. Looking at the graphs from the previous slide, note that the derivative function for f is an increasing function. Slope of the tangent lines are increasing, so the second derivative is positive. For the graph of g, the derivative function is decreasing. The slope of the tangent lines are decreasing, so the second derivative is negative. And you could reverse the reasoning to say, since the second derivative is positive for a graph of the function is concave up, and the second derivative is negative for g, therefore concave downward. So this again indicates that we're going to be able to determine the concavity of a graph by looking at the second derivative. So that's called our concavity test. If we take the second derivative of a function and it's positive on some interval, we know the graph is concave upward. And if we take the second derivative of a graph and we look at the intervals where it is negative, the graph is concave downward. Now this is very similar to our test that we did with the first derivative. We're going to take the second derivative, set it equal to 0, build our intervals, choose values to plug into the second derivative to see if it's positive or negative, and then we can determine its concavity. When we did this with the first derivative, we were testing where the function was increasing and decreasing. But when we do it with the second derivative, we're testing for concavity. Where is it concave up? Where is it concave downward? But it's the exact same type of test we did with the first derivative. The graph shows the population growth of bacteria. How does the rate of increase change over time? So we're still just analyzing this concave up, concave down concept. So we can see in the beginning at t equals 0, it's increasing rather quickly. But then as we move towards 4, 5, 6, we can see that the slope of the tangent lines are not as steep. So back in here, if we looked at the slope of the tangent lines, they're getting steeper right here. And we can see we're concave upward. And the tangent lines are below the graph, or we said earlier, the graph is above our tangent line, so it's concave upward. But do you see someplace right in here possibly that the tangent lines now would be above the graph, and they're decreasing in value? So we may say that the graph appears to be concave upward here, and then from here on it appears that it's concave downward, because the tangent lines are above the graph. And we can see it's getting closer to 0. It's leveling off there. Now this point at which it changes from concave up to concave down has a special name. It's called a point of inflection. If a graph changes concavity, the point at which it changes is called a point of inflection. Definition. A point P on a curve is called an inflection point if the curve changes from concave upward to concave downward, or vice versa, concave downward to concave upward at P. Here we have an example where we need to sketch a graph of a function that satisfies the following condition. If we looked at these conditions, let's start with part A. This first part, f prime of x is greater than 0 on the interval -infinity to 1. That indicates the graph is increasing. The first derivative tells us if the graph is increasing or decreasing. This is telling us it's increasing on the interval -infinity to 1. So I'm just going to sketch a line that's increasing up to 1. Appears this is 1 here, so we would be increasing. That's all this part tells me. Let's move to the next part. Here it says f prime of x is less than 0, which indicates it's decreasing on the interval 1 to infinity. So we just know it's decreasing. Now part B, it appears, is telling us something about the concavity of the graph, because now we're looking at the second derivative. It says f double prime, or the second derivative, is positive. We know that if the second derivative of a function is positive on an interval -infinity to -2, we can determine something about the concavity. So here it's telling us the second derivative is positive, so it must be concave upward from -infinity to -2. So we know we're increasing, and let me erase this portion right here. Oops, erase the whole thing. We know from -infinity to -2 it's increasing, but it's concave upward. And we know that this was increasing here also. Now it says the second derivative is also positive from 2 to infinity. So again, it would be concave upward. But notice, from 2 to infinity, here's 2, it's decreasing. So we're decreasing, but we're concave upward. So let me erase that portion. I know it's going to erase the whole thing, but let's, now, we're decreasing and we're concave upward. Okay. Now, finishing part B, it says the second derivative is negative on the interval -2 to 2. Now I'm going to have to go back up since I erased my graph. It was increasing from -infinity to 1 and then decreasing from 1. Okay, so it was decreasing here. Okay, so let's look at the concavity from negative 2 to 2, it says it is negative, so it would be concave downward. Now we're increasing all the way up to 1, and then we would be decreasing from 1 on. So I'm going to be increasing concave downward. Now I missed a little bit there because it does say we are increasing all the way up to positive 1, and I see that I'm decreasing a little bit there. So that would give us the general shape of the curve. And remember, I said it looks like from 0.5 to 1, it looks like it's decreasing a little bit there. It should be increasing up to that point. Now, part C. Let's see if we can get part C to show here. The limit of f of x as x approaches negative infinity equals negative 2. Thinking back to what this means, we've studied this. So if we take the limit of a function as x approaches negative infinity and we get a value, it indicates we have a horizontal asymptote. So we would have a horizontal asymptote at negative 2. So this graph would be approaching negative 2. And then the second portion, it says the limit of f of x as x approaches infinity equals 0. So again, that tells us we have a horizontal asymptote at 0, so the graph would be approaching 0. So that's the general shape of our curve that fits all of these criteria. Now you may be asking, does it matter if a graph went up like this and then back down like this? And no, it still fits all of the requirements that we have listed in parts A, B, and C. The second derivative test. This test, sometimes people use this or indicate they're using the second derivative test for finding concavity. That's incorrect. The test for concavity finds your intervals of concavity. The second derivative test helps you locate maximum and minimum values. So this here is another test to help us find local maximum and minimum values. We already have a test for this. We looked at where the first derivative was increasing and decreasing, and we could determine if we had local maximums and local minimums. This is just another way of finding local maximum and minimums. It's called the second derivative test. Suppose the second derivative is continuous near C. If f prime of C equals 0, which indicates we have a critical number, and we take that critical number and plug it into the second derivative. That's what it's saying here. We're taking our critical number, which gave us, we set the second derivative equal to 0, got this number that gives us 0 at the first derivative. We're taking that and plugging it into the second derivative. And if we get a positive value, then f has a local minimum at C. And this should make sense because if we have some function and we found a critical number, we know the slope of the tangent line would be 0 at that point. But now if we plug that value into the second derivative, and it is negative, well, that indicates the graph is concave downward at that point. And since we're testing for a local maximum or minimum, it would tell us that we have a local maximum. And vice versa, if we had here a critical number at C, well, this first derivative at that point would equal 0. But if we took that same value and plugged it into the second derivative and got a positive value, that means it's concave upwards, so we would have a local minimum. And you may be asking, what if we have something like this? Now, here f prime of c would equal 0, because the slope of the tangent line here would be 0. However, if we plug this into the second derivative, we're most likely going to get a value of 0, so the second derivative test fails at this point. If the second derivative test, when you plug in a critical number, gives you a value of 0, the test fails. Well, what do we have to do? We have to go back to the other way we were finding our local maximum minimums, looking at the increasing decreasing test. Discuss the curve y equals x to the fourth minus 4x cubed with respect to the concavity, points of inflection, intercepts, and local maxima and minima. Use this information to sketch the curve. I don't have a lot of room on the board, so I'm just going to go through the slide and we'll discuss it along the way. However, I think it's a good idea to record on a piece of paper the values that we're finding, because at the very end, when we sketch the curve, I want you to see how everything matches up to the graph that we're going to sketch. So first off, let's look for our critical numbers. We know to find our critical numbers, we set the derivative equal to 0, and then we would solve for x. So we get critical numbers at x equals 0 and x equals 3. There are the values of the function at our critical numbers. So that will aid us when we're trying to graph the function. It'll tell us where these values lie on the graph. Now, the first derivative is not undefined anywhere, so we don't get any other critical values or critical numbers. So we only have those two. Now, the second derivative for points of inflection. So we take the derivative of our derivative, and we get our second derivative. And we get, just to review here, our first derivative was 4x cubed minus 12x squared. So we're taking the derivative of that to get our second derivative. So there's our second derivative. And if we set it equal to 0, we get these possible points of inflection. Now, I call them possible points of inflection because the definition of a point of inflection is where a graph changes concavity. We don't know yet if they change concavity at 0 and 2. So we're going to determine if they do, and if they do change concavity, then it is a point of inflection. So I'm calling these possible points of inflection. All right, let's take a look at our second derivative test to see if we have any local max or mins. Now, we could do this with the first derivative test, looking at the increasing, decreasing, but we're just going to practice with the second derivative test. So if we took our Now these are critical numbers from our first derivative. We're plugging those into the second derivative. And notice, f double prime of 0 equals 0. So that doesn't give us information on if it's a local maximum or minimum. So we're going to have to go back to the first derivative test to determine local maximums and minimums. So recall that I know we have a lot of tests in here, but the increase-decrease test was taking the first derivative and finding where a function increases and decreases. Our first derivative test determines local maximum and minimums. Our second derivative test is another test for finding local maximum and minimums. And then we have the test for concavity, looking at our second derivative. So here, this is why it's indicating use the first derivative test to determine what's going on at 0. Now, f double prime of 3 is 36, which is greater than 0. So we have, and think about the concavity. If it's greater than 0, the second derivative is greater than 0, it's concave upward. So we would have a local minimum. Now back to our critical numbers. We can see where this function is increasing and where it's decreasing. And we can use now the first derivative test and look at the interval from negative infinity to 0, and then from 0 to 3. The derivative, the first derivative, is decreasing on both of those intervals. So we will not have a local maximum or a local minimum at 0. Now at 3, see the interval from 0 to 3 and then 3 to infinity. So we're looking at the value 3. It is decreasing on the interval 0 to 3, but then increasing. So if you think about a function decreasing, then it changes to increasing, we should have a local minimum. And that is confirmed with our second derivative test. Now we're going to be looking at the intervals for concavity. So the previous slide had those values which were possible points of inflection at 0 and at 2. So now we're going to look at the interval, negative infinity to 0, the second derivative. If we chose, let's say, negative 1 and plugged it into the second derivative, we get a positive value. So we know the graph would be concave upward. From 0 to 2, we could choose the value 1 to plug into the second derivative. We get a negative value, so it's concave downward on that interval. And then 2 to infinity, we could choose 3 to plug into the second derivative. We get a positive value, so it's concave upward. It's always nice to know if we have, when we're trying to graph a function, if we have x-intercepts and y-intercepts. So let's just go ahead and see if we have any x-intercepts and y-intercepts. So here we set our function equal to 0 and solve. Now we do have some x-intercepts, and recall, if we have x cubed, that means it has a multiplicity of 3 because it's x cubed. And we have learned that if we have a x-intercept that has a multiplicity of 3, the graph is going to flatten out before it goes through that point and then continue through. This happens when we have odd powers. If we had x to the 5th equals 0, we would have a multiplicity of 5. So the graph would even flatten out more than x to the 3rd. If we had x to the 7th, it would flatten out even more, but then continue through 0 and downward. If a root has a multiplicity that is even, say we had x squared, we know the graph is going to bounce. It touches down there at 0, but then goes back in the same direction. So even powers, you touch the graph and head off in the same direction, or it bounces. an odd multiplicity, you flatten out and continue through the graph. Now if it has a multiplicity of 1, we know it just goes straight through the graph. It doesn't flatten out. Okay, so we'll keep that in mind when we go to graph this. We know getting the root, when we set x cubed equal to 0, the multiplicity was 3, so it should flatten out but then continue through 0. Y-intercepts, we're going to set x equal to 0, and we would have a y-intercept at 0. Now, hopefully you have all of this information recorded on a sheet of paper so you can see how it matches up to our graph. We'll try to summarize it as we go through the graph. So first, we have our y-intercept at 0, 0. We had an x-intercept at 4 and at 0. It was a multiplicity of 3 at 0. So when we draw the graph, we'll keep that in mind. Now we had a local minimum at x equals 3. And if we look back at our concavity test, 0 would be a point of inflection. It changes concavity. We also have a point of inflection at 2. And looking at our increase-decrease test, we were decreasing on the interval negative infinity to 3. We were increasing on the interval from 3 to infinity. We were concave up from negative infinity to 0, concave down from 0 to 3, and then concave up again from 3 to infinity. So now let's see if we can put that all together and graph our function, and this is what it would look like. And remember, when we looked at our local minimum, we plugged 3 into our function to see how low the graph went. That was a relative minimum. It turns out it's an absolute minimum also. So with all the different tests that we've done, we're going to be able to graph functions using calculus. Here's another example. For this example, let's find the critical numbers first. So if we looked at the first derivative, we have 4 minus x all over x to the 1/3 times 6 minus x to the 2/3. Now this would equal 0 when 4 minus x equals 0. So x would equal 4. That gives us a critical number. Now we also have to check, is there any place this function is, or the derivative is undefined, where it does not exist? So look at your denominator. What values of x would make this undefined? We can see if x equals 0, we'd get 0 in the denominator, and if x equals 6, we would get 0 in the denominator. So we have 2 more critical numbers from where the first derivative does not exist. And here's our second derivative. And if we did the second derivative test, we're looking for local maximum and minimums. Notice f double prime of 0 does not exist. F double prime of 6 does not exist. But f double prime of 4, we do get less than 0, so we have a local maximum. Now on the other two, since they do not exist, we would go back to our first derivative test. Now I've set up the intervals here in this table, and you can see from our critical numbers, I've set up our intervals, which would be from negative infinity to 0, 0 to 4, and then from 4 to 6, and then when x equals, or x is greater than 6, so from 6 to infinity. And then we're plugging in values for each one of those factors to determine where the derivative, here, if we chose -1, we could plug that in here, we'd get 4 plus 1 is positive. Now, -1 to the 1/3 would be negative. And 6 minus a -1 would be 7 to the 2/3, which would be positive. So a positive times a negative. Our derivative is negative, so it is decreasing. So on each interval, we've analyzed what's happening with the derivative so we can determine if it's increasing or decreasing. And now we can go back up and look at this interval here and here. We are decreasing, and then we change to increasing. So now we can determine what's going on with the graph as far as local maximum and local minimums. Looking at the second derivative, we can now determine the concavity of the graph. This gives us the intervals where it would be concave up, concave downward. So we would have an inflection point at x equals 6. It changes concavity. And here's our graph. So if you have all the information recorded, you can see that everything fits this graph. Now notice at x equals 6, we did have this first derivative had at 6 was undefined. And you can see that we would have a vertical tangent. With these types of problems, it's always good to get all of your information, try to graph it, and then look at your graph. Don't look at the graph of the function before you try to graph it using calculus.